I'm such an outsider with that index. They don't even see me.
Hey, everybody. There's still some people joining, so we'll give it just another minute or two before we get started.
Hey Rob,
Hey, Hashem, how are you?
I'm very good.
Good. All right. While we're waiting for a couple more people to join, we do have two presenters on our agenda today. John D'Ambrosia, who I see is on the call, and Curtis Bowman as well, who hasn't joined yet, but
No, I'm here.
oh, there you are. I glanced right over you. I see you there. Great. Curtis, I have you up first on the agenda, followed by John. And then if Madhu's with us, or if not, we can do a quick recap on the physical infrastructure workshops. And while I'm mentioning it, I'm going to share my screen right here so everybody can see where to get it. Is on the OCP website in events for upcoming events. We have the registration link, which I'll also share in the chat, is for our next Open Systems for AI workshop, which is in the category of IT infrastructure. We're breaking that one up again because there's so many topics to cover in IT infrastructure. It's going to be broken up into 3 workshops. The first one being with a focus on silicon. And we're getting a lot of support from not only Greg and the team at AMD, but also our Open Chiplet Economy work stream with their focus and help on silicon. So please register for that. I'll be sharing out some of the presenters and a little more detailed agenda definitely by next week, but maybe even in the coming days. So register for that one and please join us. There will be we'll be operating probably on a monthly cadence. So there will be another segment of IT infrastructure towards the end of July, and then again in August. Okay, with that, I'm going to stop sharing my screen. And Curtis, are you ready to present?
Yes. Let me
Okay, great.
get my share going.
All right, we have you in presentation mode. Please take it away.
Excellent. Well, thank you all for having me today. Appreciate that. And just wanted to kind of walk through what UALink is and also how I think we work together. So let me start with, well, let's see if I can, there we go. The group itself, really robust board of industry leaders, as well as we've got 100 other members. And so we've got quite the list of people that are helping us to define what our spec is now and what the future needs to be. If you look at our history, we've been growing very quickly. We actually started just over a year ago as a promoter group, moved quickly to get the group to be something that we could open for more members. We did that at the end of October. And then we had a release candidate spec went out inside the group in February and was released to the public at the beginning of April. So from start of the group to first specification was just under a year. It had some great participation from that members that you saw. you know, the big thing about AI is we're seeing this huge explosive growth, right? And that has driven the need for compute and memory beyond what you're going to see in one GPU or one accelerator. And so what UA Link does is allow you to, create that very large GPU, right? A scale up environment really just makes many GPUs look like one large GPU. And we see that happening right now. Inference, is kind of taking a little bit of backseat while we build the training systems. But I do expect that's going to change over the next few years, and training will become the bulk of the spend. And so UA Link actually helps to make sure both of those markets can be addressed very, very nicely. We do know that, traditional and proprietary solutions actually hinder your ability to scale and become very efficient. And then finally, I think we, as two companies agree, or two standards agree, that open is the only way to go, right? You've got to be able to drive choice. You've got to help reduce the cost. And by getting the input from multiple companies, you really foster the innovation that you're hoping gets into your specs and then into the industry. And to that end, kind of what are the challenges that we see when you have a proprietary interconnect? The biggest one that we're facing today is you get vendor lock-in. And that lock-in can come in a couple ways, right? One is just, hey, we've locked you in because we're the only ones out there offering it. The other is, I've got a spec that's so complex that only one company is going to get out there to offer it for you. And so between OCP and UA Link, we're trying to drive where it's something that everybody can implement. It's easy to get there, and that helps, right? Because it decreases the costs as compared to what I show here, where you not only get the cost of buying the product that's increased, but also maintaining it, operating it becomes a higher cost for you. The proprietary interconnects end up being very siloed, so you get one point of view, and oftentimes as that moves forward, they begin to drink their own Kool-Aid. And so it slows down innovation, it complicates the way things are put together. When you have a consortium or an industry body, what you find is you get multiple points of view. It actually makes the solution much stronger. And then there's the scaling headaches that come with proprietary interconnects. If you can't use that exact solution, you don't really have a way to put it together. When you have something that's more open, you've got different vendors putting out products that meet the needs in different ways, and you can usually find your solution much easier by going across multiple vendors. So when you start to think of what we're doing here in UA Link, one is we wanted to make sure we established an open industry standard for high performance accelerator to accelerator communication. That was our key goal of going out. And obviously that is different than NVLink, but we have a very similar role. That's what we think we want to make sure we enable for the industry. And then you may have seen our announcement recently in April, where we did that 1.0 specification. And really the core of what we're trying to do is to create a low latency, high bandwidth memory semantic fabric that allows that AI workloads to work well. And we also really are looking at scale. How can you get to scale? And I'll talk a little bit about the hundreds or thousands of accelerators that we can get into a pod. So when you look at the benefits, one of them is massive scale up. Right now, with the 1.0 spec, we can support up to 1,000 accelerators. If we need to increase that because we find that a limitation, it's actually quite simple as you look through the spec. It's just allocating more address bits to it. So you could go from the 10 address bits to say 12 or 14, and that'll get you to 4K, 8K, 16K very easily as you want to go up through that. The memory semantic communications is really critical here. Been in this industry a long time, and I can't tell you how important it is that you talk to memory in the native language of the compute unit. And it's because if you don't use those load stores and atomic operations, you're doing a conversion. And anytime you do a conversion, you lose efficiency. And memory is not an area where you can lose efficiency and keep a strong performance going. The high bandwidth, low latency, that's really what it comes down to. This is what's needed for the training and inference models. If you don't have those, you really don't have a good way of making sure that you have the performance you need for your training, but even more so on the inference side. You don't get that feel of, yes, I'm getting an answer as though I'm in a conversation compared to, yeah, I put a question in and I have to wait to get an answer back. And the future of AI is going to be about having conversations or getting that immediate feedback like you would when you're working with, uh, somebody of flesh and blood. And then we do want to make sure that we're efficient. So, you'll see in some pictures here, we use the Ethernet physical layer, and that means we can use the standard cables and connectors and all the great work that's been done through the Ethernet groups over the years. But we still have an optimized stack, and so we reduce the power, we reduce the area on silicon that's required, and that helps reduce your overall costs of both purchasing it and maintaining it or operating it. And then finally, security. Right? In our world right now, security is a key piece. And so we like to make sure that we have put in our security pieces in both the hardware and in our management solution that allows you to virtualize your pods and go where you can have multi-tenants using a solution. And here's just something to kind of picture, what are we thinking right now with UALink? If you want to scale up to say 1,000 accelerators, you need to do that across some racks. Anywhere from 1 to 4 racks we think is a reasonable length for UALink. Once you get beyond that, then you're going to go to a scale out environment. And that's going to take you down the rows and across the data center, maybe even across data centers long term, where you can increase that. And that'll be very important in training models where you want to go well beyond 1,000, right, to maybe tens of thousands of accelerators. We already talked about the low latency, low power, low die areas. So I won't focus on those too much, but you can kind of see in the picture what we're looking at is there's a scale up that makes many GPUs look like one, and then there's the scale out that then allow those multiple GPUs to work in conjunction with each other. And we do know that the scale up environment is going to have a lot more traffic going across it than you expect in the scale out environment. Now, when you look at our stack, I already talked about the standard Ethernet physical layer that you see in the bottom of the picture on the right. The magic occurs actually when we get into the DL layer and the TL layer, and that's where it becomes very simple and it becomes very focused on making sure that we're optimized for a scale up environment. And there's little things like the link layer retries that get used, but there's also just simplicity here. We don't use anything extra that you might see in other stacks, and so that's why UALink becomes what we think is going to be the highest performance open standard out there for doing scale up. Now, when you look at what we can do together, right? How do we best operate together? I think both organizations are committed to the open, efficient scaling of our AI infrastructure. We also now have formalized our partnership, right? We've got our MOU in place to be able to work together and get our two communities working together. I think we do leverage the strengths, right? So UALink has the interconnect and the innovation going on there. OCP has the expertise in systems and rack architectures. And then there are some areas that I think we're just naturally aligned to work our initiatives, which, one is working with OCP on the the short range optical reach stuff, for example. And then also helping to define rack and sub-rack solutions that are easy for the industry to adopt. So these would be ones that I would like to think, whether it's a cloud provider or an OEM, might adopt these things so that it's very easy for ODMs to both design and build these for. Then, I do think, when we look at how we're going to drive that last part, how we drive the racks, we want to work with you to develop those architectures. And when I say develop, I mean not just have it as a nice presentation on slides, but actually have some implementations to show that it's easy to make, easy to deploy, and makes it so that the the adoption occurs very quickly, because it's not something that they have to go off and do a lot of testing of a design. They can implement a design that's already tested. And through that, we get that reduction of complexity, right? Because they're standard designs. It's very easy for ODMs to pick up and offer to their customer base and use their existing factories to bring those to life. Finally, as we start to look forward, one of the big areas that we're going to be pushing is that leading edge performance. And we'll want to jump into this a little faster than the industry tends to run. So the 400 gigabit solution, IEEE is going to continue to help define that, and we want to work with them on it. But we do think that while they're still putting the fine tuning of that spec together, we'll be trying to figure out how we implement it. And that's an area that we can continue to work together on. Obviously, our roadmap for future enhancements is going to help to make sure that we continue to be important in AI. We think the same thing is going to occur for OCP and its roadmap. And then if we try to look at the long-term vision, we've got to be working together to invest in the right technologies that continue to make the training and inference models working very efficiently on the hardware. To that end, UALink has some items on our roadmap. We have some of our members that are asking for not just the 200 gigabit solution, but also a 128 gigabit solution, which then can use the exact same pins that they have already committed to things like PCIe and CXL. The network collectives are really important, right? So this is one we'll be driving into the spec at the end of this year. And then finally, as we look at the industry, and as fast as UALink is moving, one of the things that becomes real important is some sort of a chiplet solution. And so we're just kicking off the effort to really define what that chiplet might be and how we want to make it a standard. I believe we'll be working with multiple groups on making sure that that's driven to industry standards so it's easy to implement. Then as I think about, well, hey, as we're working together, UALink definitely enjoys benefits of this, but also we'd like to make sure we bring benefits to the OCP community and to the industry. And so, some of the stuff that I believe that we're going to help drive in our partnership is multi-vendor interoperability, the reduced infrastructure costs that we talked about. We can actually accelerate time to market by working together, because we'll give those reference solutions. We'll be able to listen to what customers want and make sure it's in our designs up front. We'll increase the innovation. Again, listening to our members, we'll hear what they're trying to do. We'll make sure that the specifications can address that, or reference designs based on those can address that. Also, we'll be able to improve the sustainability by making sure we stay power efficient. We want to make it very easy to deploy into data centers. We want to make sure the power is used where it needs to be used. And then finally, future-proofing these investments by using these industry standards, make sure that it's easy for our members to adapt what we're doing to meet their needs. Oh, and the final slide. You know, I actually do think we're going to be shaping the future for AI interconnects. So UA Link is going to be, you know, bringing that scale up networking to the table. OCP brings their open systems and all that, you know, years of experience of the membership in that space. And then we get to the industry and engage with them as two very strong standards bodies coming together to give them the solutions they need. And that's going to drive AI forward and make sure it drives it in the way that's needed by the latest models and, you know, and the latest software. So with that, open up for any questions.
Yeah, looks like we have one hand. Pankaj, I see your hands up.
Yeah, very quickly. Thanks for doing this overview, Curtis. Great to see you again here. I had two questions really quickly. One was about memory semantics. There is some conversation in the industry about having just ability to do load store, but without the overhead of coherence in terms of chip area. You mentioned that your experience teaches you that the whole stack is needed. But could you specifically talk about what if you had load stores, but were in a low coordination approach without hardware coherence? Would that still meet what your experience suggests or leave something really critical behind?
Yeah, so in an environment like this that we're talking about with so many endpoints, I actually think hardware coherence becomes a real problem. Hardware coherence is very ignorant of what's going on. It only knows that somebody's accessing a memory location that somebody else owns. And so they have to go do the work. And that creates a lot of coherence traffic or probes going. And so we don't believe that that's the right way in a multi-endpoint environment to go, but instead push that up to a software level where it's much more aware of where ownership is important. And so coherency continues to be important, but I believe it's at a software level when you're starting to look at, you know, hundreds or even 1,000 endpoints.
Understood. Thanks for clarifying that. And my second question might sound a little bit aggressive, but it's actually genuine curiosity. When I think about a new standard, I also start to think about what are the best practices that standard is embodying. Taking your example of 1,000 accelerator system and the architecture that you have introduced, what gives you the confidence that this architecture, when built in the way that you have envisioned, will actually work? What proof points did you consult in the process? Thanks for clarifying.
Yeah. Well, that's a fantastic question. So there's actually a lot of points that have brought us to it. So, you know, let me put my AMD hat on real quick and start with we started with the Infinity Fabric as the base. And so that's been used between our CPUs and inside our CPUs, in between CPUs and GPUs for a while now. And we understand that, but then we brought the rest of the industry in and started to look at it. And they said, hey, you know, that looks like a good start, but it's a little bit too heavy in some areas. We need to offload some things. And so we had some really good discussions around what we could do with the UA Link, or what we could make UA Link by starting with Infinity Fabric. Then we have done simulations internally, and other companies have done simulations to look at, you know, what are we able to accomplish? And what we really see is UA Link gives you a very good efficient use of your bandwidth, with peak efficiency coming in around 93%. And so when you think of a 200 gig link, right, which is really 212.5, and you do the math, you actually approach almost 200 gigabits per second. of realizable, usable bandwidth. And that has been borne out by some of the other vendors that are in the consortium that have brought some of their information forward to say, yeah, we see the same thing in the, trying to reuse a solid bus that's been around, but is not optimized, right? There's too much baggage that you're bringing forward to give you the performance solution that they're looking for.
Thank you so much for the answers.
You bet.
Thanks for your questions. Thanks, Curtis. Does anybody else have any other questions?
I have one question, Rob. Does UA-Link use UEC 1.0, which got published today?
I think I missed the first part of that question.
Does UA-Link use UEC spec, which is published today?
No, no. So the two specs were developed independently. Two different groups. We do have a relationship with UEC in place, but the specs are separate, and I'm not aware of any references one way or the other between those two specs. UEC is really designed as the scale-up fabric I showed on one of those slides, and UA-Link is of course the scale-up version of that.
Okay, thank you.
Thanks, Hesham. I think we have Pekan, you have your hand up, and I think that'll be the last question before we move on to our other speaker.
Sure. Thanks, Rob. Hi, Curtis. Can you scroll back to one of your slides where you showed the PHYs, different PHYs supported? I think it was the one after the.
Is this one or?
No, maybe the 11th slide. Or maybe one after
Yeah.
this one.
I know I
Yeah,
showed this
yeah,
one.
here.
Yeah. Okay.
Yeah. So here I see that there are two different PHYs on the Ethernet and the PCI Gen 7 layer PHY, which is being supported by a common ULTL layer, but there are two different DL layers for each of the PHYs. My question is, since each of the PHYs, which is either PCI Gen 7 or Ethernet, have different link efficiency characteristics and latency characteristics, does the corresponding DL layers above these PHYs absorb the latency differences and the link efficiency differences and present a common base to the TL layer above them? Or
Yeah, go ahead.
Go ahead.
So yeah, definitely there are going to be differences in link efficiency and overall bandwidth and latency between those two solutions, just based on the characteristics of those two interfaces. We're trying to minimize those as much as possible, and so when you get to the TL layer and above, the application doesn't have to know anything about it. It's all taken care of at that DL layer, but the DL layer becomes the glue between a common TL and protocol layer and then the PHY that sits below them. And that's why they're unique, and you see them separate in the stack.
Okay, so maybe if I understand you correctly, from a functional point of view, for an end application, the UL link will look same on both the PHYs, but maybe there are some nuances which are different between a PCI based PHY, which is applicable to certain infrastructures versus an Ethernet PHY. So each of them will have some physical characteristic differences. Is that right, Samrit?
Absolutely, yeah. There will be differences at the physical layer, and you would not be able to connect a UA-Link 200 version to a UA-Link 128 version, right? They would have to be separate pods.
Okay, thank you. That was my background.
Yep. All right. Well, thank you very much. I appreciate the opportunity, and let me see if I can now get the sharing stopped.
Okay. Thank you so much, Curtis, and I appreciate the questions from everybody. John, are you ready as soon as Curtis brings down his screen here? I know when you
Yes,
screen
sir.
share, sometimes you get a really small menu bar. It's hard to find.
Yeah, I
Stop share.
think, have I stopped or not?
No, you're still sharing,
All right.
but I should be able to pull it
Where
down.
do I find? I see the share button here. Let's see.
Rob, if I share, will that
Here.
kick him off?
Why don't you
I
give it a
think I
try?
found the button finally.
Oh,
There we
there we
go.
go. Good timing.
All right.
All right, John, we have your desktop along with your dog in front of a Christmas tree.
Yeah, that's my buddy.
How adorable.
Yeah, he is. Those people who know me know I talk about my dog a lot. I'll try not to do that today.
Okay.
So, hello everybody, and thank you for the invite today, Rob. I really do appreciate this. I'm going to talk today about Ethernet's evolution to address 400 gig signaling for AI networks. I'm doing this presentation, but I'm actually working with a couple of other individuals who some of you may know from your respective organizations, Mark Noel from Cisco and Ken Lusted from Synopsys. They are both active in UA Link and UEC, as well as along with me in IEEE. Just real quickly, since some of you may not know me, first of all, I got lots of different hats that I like to wear. And for today's call, I've listed a bunch of them. I actually am the 802.3 liaison officer to OCP. I am not speaking in that capacity today. I'm not speaking in any capacity from IEEE today, but these are all of the different positions that I'm running right now. I wear. So I'm the chair of the Ethernet for AI assessment. I'm the chair of the DJ task force that's developing the 200 gig signaling that Curtis just alluded to, that goes up to 1.6. And so just so it's clear, I am with FutureWay, which is a US subsidiary of Huawei. If anybody does want to contact me, you can reach me at that email address. And as I said, I'm presenting as an individual, not in these capacities. So I've got to use the standard boilerplate disclosure here that I'm presenting my own personal views. Please note that this presentation is based on two earlier presentations that were done in the NEA E4AI effort. If you want to go and look at them in more detail, I've provided you the links there. And I should note that anything that you see me presenting today is already public. It's been published already. I don't really think I need to spend a lot of time on the need for interoperability. I think Curtis just went over that in great, I don't want to say great detail, but he really did a great job of just talking about it. And when we look at that from an Ethernet perspective, the reality is that all of these different organizations that are out there ultimately are loosely intertwined with each other, especially when it comes to Ethernet. I saw somebody put a comment in the chat field that, for example, UA Link and UEC are referencing Ethernet links. We know that different MSAs that build the optical modules, they refer to our electrical specs as well. So there's a lot of interaction between all of them. And then also I can't forget the SFF and SNIA, because they really do a great job with the connectors and form factors, right? And there's just so many moving parts in here that we have to deal with. And I think it's really important that we go into this with eyes open and understand that what we're facing in this next generation really is an industry level investment to make 400 gig happen, because 100 gig was hard. 200 gig is really hard. 400 gig, as my friend Kent likes to say it, is like, there's no, we're looking for any margin like pennies in the couch. It's really going to be a very challenging problem to deal with. In terms of, how do we get a project launched? It's good that if we just start initially with, let's step back and look at it from a little bit of a process perspective. There's a lot of discussion going on right now. I know people have said, we need to get started right away. Well, the problem is that you don't necessarily have agreement on what the problem is. So what physical interconnects does one want us to build from an Ethernet perspective? Because there are a lot. All right. And we're working right now in this E4AI assessment in .3 to figure out what exactly is needed and what the priority is. Because if we try to do everything at once, and that's kind of what we're doing with the 802.3 DJ project, you suffer as a result of trying to do everything. And I'll show you some examples of that from later on. All right, so not only are we working with ourselves, we've also been talking with all of the other organizations. As I said, we have a liaison relationship with Open Compute. We also have one with UA Link, OIF, SNIA, Ultra Ethernet. We talk quite often with the ITU, and we've basically been just sending out and making people aware of what we're doing, the need for information, because there's lots of different things that are coming in here. For example, we're dealing with different things in the fiber specs over in ITU now, and we now have people talking about multi-core fiber. That's not something that Ethernet defines. We only define a channel model that may use it. So, no one person or no one organization owns all of this. So we're in this what's called incubation effort, trying to get agreement, drive what we call consensus, to then go and do a call for interest. And in the call for interest, it's essentially you convince the people that, yeah, we need to do this. Then you move into a study group. And as you do the study group, you start to identify what your objectives are. And you start to get alignment in terms of, what are the market priorities? And that's really where you define the project itself. Then you have a task force, and then during the task force, you have baselines where you have to figure out, okay, we've said we're going to do this. How are we going to do it? And then you actually write the ultimate standard, right? And what we're seeing right now is, we're starting to get into a lot of new technologies. And, as it says on the slide, physics is physics. There's no magic answers here where people can just say, oh, if only, I could say, if only there was a better channel, if only we use less power, if everything was cheap, if it was free, it's all got to work together. And there's a lot of discussions and compromises that are going to have to be made. But at the end of the day, physics is still physics. Now, I talk about the Ethernet for AI assessment. As I said, we're talking about Ethernet interconnect for AI with an emphasis on beyond 200 gig signaling, because there's been some discussions about, well, should it be 300? Should it be 400? What's the maximum? What should we do? And I think part of this is tying into the fact that, when we talk about AI networks, yes, there's a lot of discussion about scale up. There's a lot of discussion about scale out, but there's also the discussion about the front end. And we really want to try to have commonality among all of those networks. And with that, you have a lot of Ethernet legacy to doubling at this point, right? So 200 was when this effort started back in January, but there seems to be more agreement happening towards 400 gig signaling now than there was back then. If you want to go and look at the homepage, there's information right there. If you want to join the Reflector, you can join the Reflector. I would advise, if you're interested in participating, that you join the Reflector. This is where all the meeting announcements go out. And the other thing that's really been great at this point by doing this open process is we already have connector companies and channel companies providing us, I shouldn't say that, individuals from those companies providing us with channel data that is allowing us to focus what is being simulated. So everybody's simulating the same thing and now making comparisons. So we just had our first meeting on that. You can go and look at the last meeting if you go to the homepage for May 29th. And you can see there's a lot of good discussions already happening. PAM4, PAM6, PAM8, optical versus electrical, the FEC codes that are going to be used with all this. So there's a lot of really good technical conversations that are already happening. And essentially what we're trying to do is go into it building consensus, right? And try to have answers, more agreement on some of those answers before we actually get started. Now, the big thing for this group is to understand what exactly is the problem that we're trying to do. So on the top, I've categorized things here by the different interconnects that the 802.3 DJ project currently has. So we have our AUIs, and these are our electrical chip-to-chip and chip-to-module interfaces. We have backplane solutions, which also include the cable backplanes. And these two together make up really our inside-the-box sort of interconnects. Then you have the copper cable for a box-to-box. And I think in the language that Curtis was just using, that would really be more pod to pod, because you can have the box to box interconnect in the pod. So, and I bring that up because I think as we're having these discussions, I would encourage everybody to remember that the terminology that may be common to your group or your area may be totally different than how other people think of it. And that goes for any of the analyst data that we've gotten. So we got to keep that in mind and make sure that we have a good language going forward. We also have IMDD parallel single mode fiber approaches. We have a WDM optical approaches, and then we have some coherent approaches. And as we look at this for the 3 different types of networks, right, we're not sure, are they all the same? Do they all require all the same solution? Are there different variants of it? That's one of the questions that we need to be working on. I would say at this point, the level of consensus in the group is that, okay, we all pretty much agree that the front end, the back end, scale up and scale out, they're going to need the electrical interfaces. They're going to need a backplane / cable backplane solution. So there seems to be a lot of agreement on there. On the box to box, we're starting to get some agreement there. We've had some pointers to the copper cables. We've also started to have some people talking about the PSM approach. And in that case, a lot of this stuff is just about radix, right? Because we can go to parallelism very easily in these approaches. If I were to show you my standard Ethernet slide, I would talk about how we have a family that's essentially built on solutions of 1, 2, 4, and 8 lanes. So it's very easy with a like a 1.6 capacity pipe to break it into 8 200 gig pipes. That really helps us get to a better radix. Okay, so using DJ, we're trying to identify what the future needs are as we go to 400 gig and try to understand what the different reach requirements are for each network. There may not be much reach differences, but we have to ask questions so that we know we're getting the right solution for each area. Okay, so now what I would say is that there's different areas of interest that are coming up. There was a presentation that was given back earlier this year in the E4AI, and it spawned on a interest in doing an Ethernet metadata services. And basically, you can look at it as we can't change the MAC, but we can build other interfaces to allow communications at that layer. I would encourage you to go look at this presentation. If you're interested, contact me and I'll be happy to get you in charge, get you in touch with the other individuals. And there will be another follow-on presentation on, I think it's the 22nd of July, where they're going to have the final, what we call consensus deck. In addition, there are 2 efforts that have been proposed in the E4AI effort. The first one is really the highest priority, and this is really the 400 gig per lane stuff, really targeting the scale up and scale out networks, those real short interconnects, and really focusing in on the high radix. And then we have the second effort, which is needed soon. I'll go into more detail on those in a second. In addition, there clearly is always going to be additional needs that may not get into the first or second project. I like to call this rounding out the family, because if you're not familiar with Ethernet, it seems like we have a solution for everything. You know, it's funny how I still get asked to this day, when will I get a base T connection? You know, when will I get a 400 gig base T connection? Never, I don't think. And I probably shouldn't say never, but it doesn't seem very likely at this point. But there are a lot of other options that you will get. So let's explore these different efforts a little bit in more detail. So as I said, the highest priority is this 400 gig per lane. And really, it's this whole radix issue, right? So when we look at 400 gig, we're looking at these 1, 2, and 4 lane combinations. So 400 gig, 800 gig Ethernet, and 1.6 terabit Ethernet. We're looking at the electrical interfaces. So for the chip to chip and the chip to module to the pluggable front panel. Excuse me. We believe that we'll have pluggable modules for both optics and the copper interconnect needs, but we're also looking at CPO and MPO implementations. And we believe the CPC implementations will be common for the electrical channels. For the copper cable and back planes, we've talked about a meter direct attach. But there is some question if something less than a meter, say 3/4 of a meter, may be acceptable to some. And when we say that, we have to remember from a cable perspective, you have budget for the cable length, but you also have budget that you have to worry about for the 2 hosts. So we are already thinking about, are there going to be alternatives to a passive DAC that may be considered? And then for the optics, you know, you're kind of looking at this more as a fundamental technology. Let's get the 400 gig optical going. And in that case, it's 1 lambda per fiber, and then you can do parallel fibers. Once again, this allows you to get to the highest radix that you need, but also if you need bigger pipes, you can still go to 2 lanes or 4 lanes if you need to do that. And when we talk about the fiber, you know, once again, I'll come back to, well, what are the reach breakpoints? You know, and is there a common solution? Because a lot of times, you know, it may not be, you know, one application might be 50 meters, another one might be 100 meters, and really at that point, the cable isn't adding in a whole lot of problems to the solution. So maybe one solution will be able to satisfy both. Now for the second effort, there's continued development for the 400 gig signaling. So we'll look at going to 8 lanes, and we'll look at expanding out to a 3.2 terabit solution for both the copper and the optics. So we can imagine longer reaches, so intra-building, inter-building. We can imagine different FECs for these different reaches. We can imagine different SMF channels. As I already alluded to, we've had some people talking about multi-core fiber already. And then we also have the open circuit switches has been another consideration. And then what about something else other than SMF, right? Maybe there's multimode out there. Maybe there's something else that we don't even know about yet. And then we've got the active cables that we may not do in the first effort. That should be effort 1. From an additional future needs, I'm putting MF here, even though I just mentioned it. The reason why I'm doing that is because they are actually just getting started on 200 gig over MMF in July at this upcoming plenary. So it really would be a matter of timing as to when MMF would be ready to jump to 400 gig. I'm putting that out there basically because I want those people who are interested in MMF to hear what I'm saying and start working on bringing in input, because I think like any organization, we are contribution driven. And I always leave this other there because, you know, Ethernet evolves and we find people wanting to do different things, right? I look at, in my time, all the new things that have happened. You know, there was a time when there was no backplane in Ethernet. I was part of that. That was my very first project, to be honest. So it's just very interesting to watch Ethernet expand and evolve to satisfy the needs of the industry. Now, I want to point out that different projects have different kinds of personalities, and this is just a history lesson, if you will. You can look at it as new rates, and by rates, I'm really talking about Ethernet rates versus developing new PHYs. And a new PHY may actually leverage a different signaling rate, but it may not be a new Ethernet rate. And those projects do have different aspects to them. Okay, so when you get into a new MAC project, everybody wants to get into a new MAC project. So what winds up happening is you have a longer duration, you have longer study groups, there's more baselines that you have to worry about, and because you have more to deal with, it generally takes more time to write the draft. And as I said, it targets more different types of PMDs. If I were to, right now, the DJ spec, when you look at all of the electrical specs and all of the PMD specs, you're talking about 32 different specifications. Okay, that takes a lot of time. It takes more time than what I think people really want in terms of the signaling for the scale up and scale out networks. So, you know, if we're going to enable this rapid progress and be able to move fast, we're going to have to focus in on consensus building and market education and drive a prioritization of what has to happen first and what can happen later. Okay, now, as I said, we were talking before about the 400 gig signaling over the electrical and some of the optical, and you can look at that as kind of a baseline. And if you look at these projects, for example, the 802.3 BY project right here, and the CU project and the CK project. Now, the CK project is an anomaly in terms of the task force draft because they actually went into task force right around the time at the beginning of the COVID pandemic. So not only did they have a challenging problem to deal with, 5 years ago, we weren't as well versed working with the different electronic tools. So they had to learn how to deal with developing a standard in that environment. So I think if you're looking at the draft time, that's probably an anomaly. But I think you can see here that the study group duration took less time, all right, than the other three. So BA, BS, and then the DF, which all took a year. And that's because everybody wants to do everything, right? And it's very hard to say to somebody, oh, no, we don't think we need you at that point, because everybody wants to get in. They don't want their particular solution left out, all right? But if you have a targeted project, you can move very fast here. And that carries forward right into the baseline selection. Now, in the case of the 100 gig copper, the 100 gig cable, the CK project, that took a little bit longer. It was a very challenging problem. So they ran into some stuff there. But you look in general, there was like one meeting, they had all their baselines done. Another group, the CU group, was 4. But if you go and look at the new rate projects, well, 5 was the quickest, but then 9 to 12, right? So you're going to expect those bigger projects to take a little bit more time, and then you can follow through and say, the same thing is true when we start looking at generating the draft. All right, so the idea of doing everything together probably isn't going to be the best way for us to get to solutions quickly that people need. I know we've had some discussions with people, and we said, hey, what's the first priority? And in general, they do say scale up, but they hedge and then say, but really I need everything because I build networks, right? So we're trying to figure out how can we satisfy everybody in the quickest way. So taking into account what I just said, all right, I've kind of tried to scale this. And we have, first of all, the NEA, which is doing all of this consensus building and incubation of efforts. And that's an ongoing effort to develop new projects related to Ethernet for AI. So if I think that this study group for effort 1, remember that was focused on existing Ethernet rates using new 400 gig signaling and not having everything in there. In general, the study group could happen, and we think it could move very quickly. And this is what we're trying to look at, is like, how do we reduce all of these durations? Okay, so the study group for obviously the 400 gig effort 1, as I called it, would feed into then that discussion that's happening in effort 2, which is really the new rate, which would leverage the 400 gig signaling. All right, so we're thinking these are 2 efforts that are going to happen in a very short time, related to each other, but different. Okay, and that's important from a scheduling perspective, which you can see here, that a baseline adoption we think could happen in the first effort before the second effort is even through its study group phase. Okay, and then the task force draft, well, I've made that longer for the other effort based on what we saw for CK, a challenging problem, blah, blah, blah. That is definitely going to feed into then the draft selection or the draft work that we do for the new rate of Ethernet. So we're basically using the first effort to satisfy industry needs, but also then to be building blocks for the next rate of Ethernet 3.2, right? Because the problem is that if you throw all of this in together into one project and one timeline, you're not going to get the things as fast as you would like. And let's not forget, I talked about this before, that stuff all feeds out into the industry and all of the different implementation specs. We just heard Curtis talking about UA Link. I'm sure Curtis wants us to make this as quickly as possible for him to then use in UA Link. Same thing for UEC. And I'm sure OCP as well is just wanting solutions as fast as we can. And that's the process that we're trying to figure out and drive at this point. Okay, so summary. There's a lot of people on this call today that belong to OCP. IEEE and OCP, we have a liaison relationship. You can leverage that liaison relationship as an organization if you wish to send us something. Or our meetings are open to all individuals. If we do have a meeting that has a face-to-face component, these typically do have a registration and a fee associated with them. But a lot more of our calls right now in the NEA the E4AI effort that I talked about are being done with electronic only meetings, and these do not have any registration or registration fees. Okay. And then I'm going to also say that any input from the OCP or any individuals on this call that you want to help us to address this problem would be welcome. And I guess the last thing here, Rob, I really need whoever is going to be Bijan's replacement to work with, because there's a lot of stuff that we were talking about. And I'm, as you know, I wasn't aware of this call because I was focused in on 2 other calls that I got from OCP. So I haven't mapped the OCP structure yet in my head. So I'm not sure who to talk to follow up with from Rob's, from what Bijan was doing.
Yeah, no problem. I'm the point of contact for this initiative. So you can continue to communicate with me. And then on the foundation team, we have Cliff and James. They're also part of,
Can
from
we
our
catch
side.
up on that offline and just make sure I have all the email addresses and phone numbers?
Yep. Yeah, absolutely. Let's line up on that.
Okay, perfect. With that, I am done, and I'll be happy to take any questions that anybody may have.
Yeah. Hey, John, this is Robert Hormuth.
Hey, Robert, had a long time no chat, buddy.
Likewise. I hope you're doing well.
Yes,
Hey,
sir.
quick question. What do you think the fastest the 400 gig could get done in IEEE here?
The fastest. So I think the study group can be very fast. The baseline adoption may be a little tricky. So I actually think we could probably get a study group done in 1 cycle, if you will. Baseline adoptions, I think we are seeing some, we're seeing some consolidation of viewpoints. There seems to be a lot of focus on PAM4 for the optics. The PAM on the electrical is raising some more issues though. And there's some debates in there. So I think that could be a sticking point. So I think the baseline adoption could take a little bit longer. Okay. So let's just use the 9 to 12 month there. So that's 16 months. And then the draft that can take a year and a half. All right. So we're probably looking at 2.5 to 3 years. But I will say that I do think we're also running into some other issues being ahead of the game as we are. I've had some conversations with the testing people, and some of the testing equipment and connectors they're not going to be available in volume for the test equipment in production until 2027. There's going to be
the reason I'm asking, John, is this. The world of AI is innovating at a new pace than we've ever seen before.
Yep.
And people are not going to, my fear is people are not going to wait.
Yeah, I understand that, Robert. That's what we've been trying to figure out.
Yeah, I mean, you know what happened with 25 gig.
Yep.
I don't know that we necessarily want to see an MSA splinter group go off and accelerate. And so it's really upon IEEE, I think, that to really hone in the process and get it done as fast as let everybody help get it done as fast as possible. They show the willingness to move faster than they've ever moved before.
Yeah, and Robert,
my fear is we're going to get some splinter MSA 400 gig that are, I mean, maybe the 25 gig wasn't so bad. At least it was only one splinter group. I'm afraid you could get multiple groups here.
Here's what I'll say. We're very aware of this. Okay. In terms of starting, so for those of you who don't know, I've led every speed development since 10 gig happened. Okay, so I did 4100, the 200, 400, and now the 801.6, and now I look at this effort too. That's going to be mine. Okay, so we have never started this early in the process, ever. I can actually say that the consensus building started before we even had the task force review and baseline selection done. That was after OFC 24, right? So a lot of organizations work together with the the TEF, and then the OIF's done stuff, and the OCP has done stuff to drive all of that interest going. There's a lot of, like I said, we've got channel models even at this point, which is ridiculous to think about in terms of what's happened in the past. It's so quick. So we are moving faster than we ever have. But
Yeah, don't get me wrong, John. I actually
no.
recognize that.
I hear you. That's
I
why
recognize, because last fall I was really worried, because it was like the proposal was to do a year-long study of the problem.
So
And it seems like we short-circuited that to like 90 days, and so I can definitely see the speed picking up, which is really good.
yeah, it definitely is picking up, but there still is a lot of
Yeah.
questions and debates that have to happen. And the active cables is one thing, the whole CPO is another thing, and getting agreement on some of that stuff. And quite honestly, if I go back to this slide, where is it? This slide right here, we've gotten minimal input on some of this stuff. I really just said, okay, I don't think anybody's going to argue with this inside the box, right? Because we know we're going to need chip to chip, chip to module connections and some sort of backplane style solution, whether it's traditional backplane or copper. It's getting people to, there are challenges here, not just the physics, but you have people who are going to not want to commit to anything because it's so early in the process and there's no skin in the game at this point, right? So there are some challenges here. So I hear you, and all I can say is that's why I'm here today telling you how we're trying to attack this. And I think the one thing I want everyone to take is I don't want people to think that, oh, if they miss effort one, there's, we've got to get everything in effort one. If we pilot everything into effort one, you have a DJ style project, and that's going to be much longer. So I really think that this focused approach and develop the base technologies that we can use elsewhere will help us to move faster. But with that said, the physics are going to be the physics, and that's what the groups are going to have to overcome.
Yep.
Hey, John,
thanks.
Yep.
Thanks, Robert. John, is this a presentation that you can share with us, and we can kind of send out a call to action?
Yes, it is. I did notice a couple of things I want to clean up, so I'll send it to you afterwards.
Okay.
If that's okay. I just
that'd be
noticed a
great.
couple typos.
Yeah, no, thanks for doing that, and we'll get it circulated, with our mailing list, and then also if you have a call to action on some of these items that you can outline as part of the body, I can add that to it.
And Rob, so Bijan did do a liaison presentation to us back in, I think it was March, not February. I'll double check. I'll forward you the link to it in case. I don't know how well you guys got communicated internally.
No, that'd be great to make sure we're aligned on that side too, and we can pick up where we left off.
Perfect. Are there any other questions? I don't have the chat window open.
No, there's nothing in the chat window. I don't see any hands raised, and we are past time, so it does look like some people had to drop off. That's why I want to make sure this recording will get posted, and then I also want to make sure people had access to your deck.
No problem. Thank you, everybody. I appreciate you taking the time.
All right, thanks for everybody who stuck on here for a couple minutes past. And please register for the upcoming workshops, and we'll catch you next time.
Right. Appreciate it, Rob. Hey, thanks, John. Good seeing you again.
Yep. Good talking to you, Rob. Take care.
Thanks,
Rob.
everybody. Thanks,
I'll
John.
set up a call with you sometime tomorrow, okay?
Okay, sounds good.
All right, bye.